like I said, today and tomorrow are more or less going to be a review of what we did in grade 11. So I'm probably not going to go in as much detail as I normally do with other years. If, though, something does not seem familiar, please stop me. Okay? Because I don't want to be one of those teachers who makes assumptions that you know stuff. But I kind of am assuming that you know it, because I did kind of teach a lot of this to you in the past. But please stop me if it's like, whoa, 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 whoa. So let's start with some review. One of the things that we worked on a lot last year in the trig unit was angles in standard position. And for those of you guys in my physics class, we use that concept a lot. Let me just review a little bit here. If something's in standard position, it means that one of the sides of like your triangle is along the positive x-axis. And in physics, we denote this as 0 degrees. Or we sometimes say that that is east, because east is that way. That makes sense? That would mean then that up here, this would be 90 degrees, which would be considered north. This would be 180 degrees, which would be west. And south at 270. What if I gave you 360 degrees?
That would mean 0, wouldn't it?
It would really mean 0, which means that you just went all the way around the circle. So if you went all the way around a circle, you're actually back facing east again. Does that make sense? This terminal arm is defined then as like the other part of the triangle, I guess, one of the other angles in the triangle, and it can lie in any of the 4 quadrants. I'm going to fast forward to some different slides here. Actually, this one's probably good. Here, the positive arm is still facing towards 0 degrees here, but now the terminal arm is off in quadrant. Do you guys know the quadrants, by the way? Yeah, this is 1, 2, 3, 4. So if it's in quadrant 2, here's this angle. Estimate this angle here.
110 degrees.
Sure. I'd say from here to here could be 110 degrees. Okay. That being said, we have a term we use then called a reference angle. And the reference angle is this little blue angle right here. Of course.
Hello?
Who is this?
Okay, just one sec. Can somebody go check to see if it's part A or part B? If it's even in there? I don't think it is actually.
There's no card in there.
I'm disturbing it. Is it though?
There's no card in there.
We don't have the card.
All right, tell them that they need to check themselves next time because they just disrupted it.
Okay. Do you know if it's A or B?
I have no idea.
I don't know.
Either way.
Don't know.
Please.
What is that?
B.
I have no idea.
Go away, Noni.
Fair enough. Okay, do you guys remember these termed reference angles then?
Yeah.
One of the key things about reference angles, is my board just died here. There we go. Is that the reference angle is, by convention, made against the x-axis so that this would be the angle right here. It is possible to draw a triangle like this with an angle right here, but by convention, just to keep things straight, we always go with next to the x-axis. Does that make sense? So if this guy was 110 degrees, what's your reference angle over here? 70. Okay. Down in this quadrant right here, this angle could be like, say, 230 degrees. If this was 230 degrees all the way around, what's my reference angle?
40.
50.
270.
No, 180.
Because the reference angle would be from here, it would be this little bit right here.
Never mind.
So then 180 plus an extra 50 would be 230.
I thought it was the other way. Reference angles.
So the reference angle is always from the x-axis?
Always to the x-axis.
Okay.
Just as,
So
so like what we don't want, this guy right here would not be the reference angle.
we can't have it like through the x-axis.
Yeah, like going all the way around through the x-axis would be from here to here is 50.
Like, could we have the blue line go like through the x-axis through the y-axis?
I might need you to draw me that. I don't know what you're saying.
I think he means all the way around.
Like say you had angles.
Like the other 130.
Oh, like down in this quadrant here?
Up here, no, like could we have it
Like the extra 130%
you
around.
always want us to stop at the x-axis, or do you want?
Like a
Like for this guy right here, then we have to figure out the extra amount that goes to the x-axis. Whereas since this one went through the x-axis, we got to figure out the amount that gets us backwards to the x-axis. Does that make sense?
Yeah.
Okay. And the answer to that is no, we don't reference to y-axis. Okay, I threw in a diagram here that maybe can help explain why we've gone with these conventions. Okay, the reasoning actually for how this worked has to do with the sun. The sun typically rises in the east and sets in the west. That makes sense? Well, okay, technically the Earth goes around the sun, but at least from our perspective, the sun would start over here at the beginning of the day. The sun would then rise up, do kind of a over-the-top motion, and then come back down and set in the west. Therefore, east was then denoted as 0 degrees, and west was denoted as 180 degrees. And that's the reason why we've chosen that. Because a good question is, well, why is north not 0 degrees? Because north usually seems to be a good reason for that. But does that make sense as to why? So, not that that really matters or anything, but that's why this is 0, this is 90, this is 180, this is 270. You just got to kind of flip the circle a little bit here. Does that make sense if you can envision that? Okay. I got a lot of pictures just to hopefully reinforce what I've talked about. Here's all the quadrants. Okay, and you need to be able to figure out positive and negative angles. For example, if this guy right here was, let's say 110 degrees, you could go backwards the other way as well. Did we talk about this last year at all? The idea of maybe having a negative angle? Okay, so maybe here's something that's new then. If you go this way 110 degrees, it would be like going backwards 250. How did I figure out that value of 250? Yeah, because it adds to 360, right? So 360, I'll just say that these two numbers have to add to 360. The only difference here is with a negative number in front, it just means we went backwards. That's all. Why? Well, convention is that if this is east and this is west, the sun goes this direction here. So that's why those were denoted as positives. But if you were to try to go this direction here, then it just means you have negatives. So this way is positive, this way is negative. So if I were to use the term counterclockwise, do you guys know what that means? Yeah, and then this way would be clockwise. So counterclockwise means a positive angle, and clockwise means a negative angle. You okay?
Sounds like the chair.
Okay, just more pictures about reference angles, just to make sure you guys are all clear on this. Even if you were to be down in these bottom quadrants right here, the reference angle is always made compared to the x-axis.
What about to the other side? Like once you're in the new quadrant, then you go to whichever x-axis that is in. Like in
Yes.
the last one and the fourth one, you wouldn't go back to the other side.
No, you wouldn't go back to here. You'd go, it's always an acute angle, so it's always like the smallest angle possible here. Because you're right, you could find an angle to here, but that's not a smaller than 90 degree angle. Kayla.
So, when you said the reference angle is always made to the x-axis, you're just saying that, like, I don't
Like
understand.
from this line to the x-axis is the reference angle. From this line to the x-axis is the reference angle. Here's what's wrong. From this line to the y-axis is not the reference angle. Does that make sense?
Yes.
Okay. Okay, one more picture, then I'll show you something that's hopefully kind of new then. If we were to estimate some angles here then, I just want to show you three main types here. Here's a very basic angle. If I had to guess its angle, I'm going to go slightly more than 45. 50 probably makes sense though. Okay, so that's a very typical angle there. But here, since we're going clockwise now, what does it mean the angle has to be? A negative. So it's almost like this is 0, this is negative 90, this is negative 180. Does that make sense? Sure, yeah, you could say like negative 120, whatever you think it is in there. But the point I want to make on this one is that if you go backwards, it just means we count it as a negative angle. That's all. One more thought here. Is it possible to go around the circle more than once? Sure, I guess. It just means that you've like spun around all the way to 360, and then you've gone a little further.
So like negative 380.
Well, no, it's positive because you went this way,
How
but
would you know
positive 380
So
works.
the way the arrow is pointing.
Do you see how the arrow is pointing
Yeah,
like
well, they're always
here?
arrows.
Yeah, I'd have to give you something like that to show you.
If the arrow was like on the other end, like right
Sure, if the arrow was like here, and then it wouldn't have started here. It would have to be like here to there, perhaps. That would mean a negative angle. Okay. So I guess the point I want to make on this one here is you can have angles greater than 360. It just means you go around the circle more than once. People who this sometimes applies to are like snowboarders or skateboarders. You guys ever heard the term like doing like a 1080 or a 720? It means that they went around this, they like around the circle twice or 3 times. Do you guys know those terms?
No.
Oh, never mind then. If you're a snowboarder, maybe you'll recognize like 540. That's like an all the way around the circle and then like backwards.
Like how many times you go around?
So like, well, like a 540 would be like all the way around in the circle, and then, but then like you're going backwards down the hill.
Oh, okay.
Oh,
Does that make sense? Because like it's all the way around once, plus like halfway, then you go backwards.
I know.
That makes sense.
Anyways, if you're a snowboarder or a skateboarder, I get the impression you probably know what I'm talking about. If not, then don't worry about it. Okay, so far, more or less review?
Yeah.
Excellent. Now something new. This will be new. Okay. Here's the big difference between grade 11 physics, not physics, we're in math. Grade 11 math and grade 12 math. From now on, your calculator, you know how there's like radians and degrees in your calculator? We're going to work with radians from now on.
How do you change that?
What is a radian?
Okay. So, the point of my rest of my lesson here is to explain to you what a radian is, and 2, to give you as good of a reason as I can as to why we work with radians instead. Because the math is not different. I liken it to like a different language. We've now learned how to do math in English. We're now going to learn how to do math in French. Only rather than English and French, now it's radians and degrees. Okay. Let me give you. Okay, story time. Okay. Degrees as a measure of figuring out angles is a lot more recent. Radians are actually probably the first measure of angles. Okay? And here's how a radian worked. If you have, say, a circle, and you cut out like a sliver of pie, the first way, at least that I know of, that angles were measured were based on this concept here. If this radius right here is also equal to this radius right here, and is also equal to that same length along the edge here, that was considered to be a radian. I like to call a radian a perfect slice of pie. Okay? Because what ends up happening is this side right here, say this was like 2 centimeters. This side right here was also 2 centimeters. This side right here was also 2 centimeters. They called that 1 radian.
What happens if it's not?
We'll work on that in a second. Okay, let me get to that in a second here. Okay. On my next slide here, I got a slice of pizza. Think of a radian then as like the perfect slice of pizza, where if this was 14 centimeters and this was 14 centimeters, this edge right here would also be 14 centimeters. Okay, that's considered to be a radian. If you were kind of chintzy with your pizza slices, and someone made it so that your slice of pizza was only this big, it wouldn't be a radian. Because this would be 14 centimeters. This would be 14 centimeters, but this right here might only be, say, 7 centimeters. How many radians is that? Half. That makes sense?
Just happens.
So it's dependent on that one side?
It's dependent on however big the radius is, and this right here is called an arc length. We use A for it.
So you can just divide it.
That's all you do, you divide the two.
How would you know?
That's the formula here.
Jeez.
Okay, give me a second here to keep, let me give you a little more first, okay? To find out how many radians you have then, take the arc length and divide by the radius. If the arc length equals the radius, you have 1 radian. If the arc length is double the radius, you have 2 radians.
Wait, so like the little like theta sign is.
This stands for radians, which normally for us has been angles, but the angles we work with are no longer going to be measured in degrees. They're going to be measured in terms of this perfect slice of pizza. Birdie.
So the arc length, that's like the curve on the outside.
Yeah, the arc length is the curve on the outside. By the way, I don't know why I called this radium. This is supposed to be radius. I don't know why that auto-corrected. Radium is like a chemical. Someone else had a hand up. Okay, let me try one more example here just to make sure you guys have got this figured out. So here's your pizza, and let's say that rather than getting that perfect slice of pizza, someone is particularly greedy and decides to make this their slice of pizza.
That's like my kind of pizza right there.
That's their slice. Okay? Can I teach? Okay. The only thing you need to figure out for how many radians there are, you need to know this length right here. So why don't I say it's a 14 centimeters again? I just picked that number
Are
up.
both legs?
And they should both be the same because they're both radiuses.
Are we gonna work with pendulum and all?
No, they have to be, because based on like how a circle works, this is a radius, this is a radius. So yeah, unless it's an oval or something, they have to be the same. Then we'd have to measure how far it is along the edge here. So why don't I say that along the edge it was 30 centimeters? How many radians would you have then?
2.1.
Yeah, you'd take 30, you'd divide by 14 for. Good job.
Stop it, kiddo.
So essentially, you have 2 and a little bit of a perfect slice of pizza. Okay. This was probably the first way that we measured angles, radians. Here's the problem with radians. They're hard to conceptualize when you teach kids about angles. And so eventually a new system was developed called degrees. And degrees works really well because in a circle there's 360 degrees. One of the reasons why 360 degrees was chosen is because if you go back to my very first slide, the Earth goes around the Sun in 365 days.
Oh, why?
So it's not complete perfect.
It's not perfect, but it was pretty close.
But there's the leap.
And that actually comes into part of that explanation. Essentially, every day that the Earth goes around the Sun, it more or less goes around the Sun 1 degree. Kind of. It's not perfect, but it's pretty close. Okay, that's one of the reasons why they chose 360 for degrees. Another reason why they chose 360 for degrees is because 360 is divisible by almost every number. 360 can be divided by 2, by 3, by 4, by 5, by 6, not by 7, ignore that, by 8, by 9, by 10. Like 360 is like divisible by almost every number. Okay. So those 2 reasons were why degrees were eventually invented as a way of measuring angles, but they probably weren't the first way of measuring things. That makes sense? Another reason why degrees are useful is that when you're talking to like little kids in grade school, if I were to ask you to estimate, this board is glitching out on me. If I were to give you an angle like this, could you estimate how many degrees it is? And I'd say, yeah, you could probably guess it's about 40 degrees. If I were to ask you how many radians it is, though, that's a little tougher. I know it's like less than 1 radian, like it's not quite a perfect piece of pie yet, but it's kind of hard to estimate. Does that make sense? So
45 degrees.
45 would be like exactly halfway, I think.
So would that be, yeah, would that be a radian?
No, a radian is more than that, actually. If you look a little further on in my slides, actually, give me a second. We've actually calculated that 1 radian is 57 degrees. Okay. And I have a proof for this. I want to show you why. Okay. Here's the proof. The circumference of a circle is 2 pi r. Do you guys remember that formula? C equals 2 pi r. Let's say that you were talking about the whole pizza. Okay. The way the formula worked is you do your arc length divided by your radius. But what if your arc length is the entire pizza and you divide by radius? what would happen to radius? It would cancel, and that means that your arc length would be 2 pi. That's how many radians you'd have.
So if you did
Okay,
360
so here's what that means. 2 pi worth of radians is 360 degrees. So if you then were to take 360 and divide by 2 and pi in a bracket, by the way, you'd get about 57 degrees for what this perfect piece of pie has.
So
Yeah.
if you divide 360.
If you did 360 divided by 2 pi, you should get 57-ish. But you gotta divide by 2 pi in brackets. So like, do this. 360 divided by 2 pi, but put it in brackets. And it should be basically 57 degrees is what a radian
That's
is.
like when I did 360 divided by 57 and then divided by 2.
You got pi. Yeah. So let me just recap that proof there, just to make sure this makes sense. Okay. The circumference of a circle is 2 pi r. But if radians means take the arc length and divide by radius, you divide, r cancels. What that means then is 2 pi radians equals 360. So that means 1 radian equals 57. Here's a good diagram to help make sense of this. If this is a perfect piece of pie in a circle, you can get 1, 2, 3, 4, 5, 6 perfect pieces of pie, and then there's just like a little bit left over, and that little bit left over is 6.28. The reason why? 6.28 is equal to 2 pi.
Oh, you put zeros. That really screwed up.
What? The last arc is.
Well, okay, so this little bit right here is 0.28. So 1, 2, 3, 4, 5, 6
We're like, what?
plus a little bit equals 6.28.
Oh, that makes sense.
Okay, here's the issue with radians then. Radians suck because they're not nice round numbers like degrees. Degrees was developed to make it nice and easy to work with, but radians are all about how many of these perfect pieces of pie you can fit into like a circle. Okay? My goal now is to help transform your thinking from always working in degrees. It's like learning a second language now. We're now going to convert from degrees to radians. For those of you guys in physics, you're going to have to be really careful because in physics we work in degrees still. But for this math unit, we're almost exclusively going to work in radians.
So, make sure we're
Okay, well, so make a habit of every morning, switch back to degrees. Does that mean we should start counting?
All the time.
the radian curve.
Okay, let me give you guys some examples here then. We need to practice this. Okay, here's what this means then. We've discovered there are 360 degrees in a circle. There are exactly 2 pi radians in a circle, about 6.28 radians. Okay. Doing some basic dividing calculations then, 180 degrees should be pi, because you divide by 2. 90 degrees, if you divide by 2 again, is now pi over 2. And 45 degrees is pi over 4, because if you divide over 2 by 2 again, it's now over 4. Does that make sense?
Oh yeah, the corner.
Yeah.
Okay, let me see if this makes sense then. On a circle, this used to be 0 degrees, this used to be 90 degrees, this used to be 180 degrees, this used to be 270 degrees. Well, from now on, we're going to label it differently. 180 is going to be known as pi. 90 degrees is going to be known as half of pi. Yeah, this one will be known as basically 1.5 pi, which is 3 pi over 2. And all the way around the circle will be 2 pi. Basically what it means is that each quadrant is a pi over 2. This is a pi over 2. This is a pi over 2. And this is a pi over 2. In terms of how many radians everything is.
What was 270?
270 is 1.5 pi, or 3 over 2 pi. Rather than working with decimal numbers, though, the convention is to talk about things in terms of how many pies there are.
Why is it called pi?
Like, why we call it that? Because that's a Greek letter. Pi is a
It
Greek
makes me
letter.
think of pie, and I was hungry. But it makes sense. Is that why they're called pie pie?
I don't know. Maybe because it's round
Yeah.
and it fits with circle stuff. I don't know.
Pizza has pie.
Okay, let me give you some examples because I think we actually need to do some examples here. Let's say I wanted you to convert from radians to degrees or degrees to radians. Okay. This is probably the most important part. Okay. I think I taught all of you guys chemistry, right?
Yeah.
Sorry, Jack. Minus you. I showed you guys in chemistry an idea here. If I were to give you, like, say, 160 grams, and then you'd times by, like, say, moles over grams. Do you guys remember doing this? Okay. The ratio you guys need is this. There are 360 degrees in every 2 pi. Or there's 2 pi in every 360 degrees. Depending on which one of these two fractions is useful, we're going to multiply by this ratio. So let's say we started with 30 degrees. I'm going to multiply by 2 pi over 360 and figure out how many radians there are. Because then the degree sign on the bottom would cancel. Does that make sense? What happens when you type that in your calculator?
Where's my pi sign?
We have to change it, right?
You have to put in
Because this is how many radians it is.
I got 0.25. I mean, what the heck? I got 0.5.
Are we supposed to change it? No, like, is that doesn't matter.
No, don't worry about changing that just yet. I'll talk about that in a bit, though.
Oh yeah, I got 0.5, 2.5,
Conlon?
How do we know like multiply by 2 pi over 360?
Because in 360 degrees, there are 2 pi, or about 6.28, worth of radians. The proof for that was because circumference is equal to 2 pi r, and then because you have to take that and divide by a radius, there are 2 pi worth of radians in 360. So that's our ratio we work with.
Wait, what?
Can you guys give me a few more examples?
Can you do that one?
Okay, let me just draw this out real quick here. If I were to draw a circle, well, you don't even need a circle. If I were to draw 30 degrees right here, is this going to be is this going to be enough to make that perfect piece of pie? I'd say no. If someone gave you a 30-degree slice of pie, they're being kind of cheap because that perfect slice of pie is about 57. So is this going to be a full radian? No. This should be less than a radian. It's basically just over half of a radian.
So you do 2 pi divided by 30.
Say that one more time, Nicole.
It'd be 2 pi divided by
360. Like go 30 times 2 pi divided by 360? We're not on the same page, are we?
30 times 2 pi.
Divide by 360.
Okay.
Does that work?
Yeah, better.
Okay, here's the issue, guys. Is everybody okay with getting the answer 0.52?
Can we just call it a rad?
Okay, first thing, there are no units for radians. So if you want to call it radians afterwards, just to remind yourself what we're talking about, that's fine. But typically we don't call it radians, we leave it with no units. The other thing is that this 0.52 had to be rounded. Typically we don't like to round. So what they do is they talk about it in terms of how much pi there is here. So I want to show you how you can do this on your calculator. Just give me a second. It takes a little while to like rejig your brain to stop thinking about degrees and to think about radians. It's going to take a couple of days, but I promise you'll get there. When you guys did 30 times 2 pi over 360, it should have given you this completely irrational number. Okay. Instead of throwing pi in here, do this. 30 times 2, don't times by pi, and divide by 360. Okay. Now take this number, and do you guys know how to make it a fraction? You guys ever seen how to do that? Go math, and then fraction.
Oh, 1/6 pi? Is that what you call it?
Okay, and this is where I want to go with this. This is actually better referred to as 1/6 of pi.
makes it look really pretty. It's not.
Okay, it should get you a fraction. The only reason it wouldn't give you a fraction is if you leave pi in your calculator. Okay, let me try a few more examples, okay? This is one of those things where I think I need to do it a few more times. Okay. So, for this guy right here, 120 degrees, before I even start, can we do some estimation here? 120 degrees would be in this quadrant right here, give or take. How many perfect pieces of pie should you be able to fit into that? Just over 2. If a perfect slice of pie is about 57 degrees, I should be able to fit about 1, 2 of them in there, and there should be like a little sliver left over. Does that make sense? Now let's prove it. Take 120 and times by 2 pi and divide by 360. The reason why that works is that there are 2 pi radians in 360 degrees. What do you get when you type those together? 2.09? Here's the problem though. That number there is an irrational number with decimals. And typically we want to avoid that. So, make it a fraction like this. Take 120 times by 2, but don't times by pi. And then divide by 360.
I don't understand why that works.
Make it a fraction, and now what you've got is 2 over 3 of pi.
Oh, that makes sense. Because it's like almost.
Okay.
Bottom line is small. It's like-
Okay, let me draw this out here. If this was 0, and this was 90, and this was 180, and this was 270, and I said we were talking about 120 degrees. Okay. 360 was also 2 pi. Does that make sense so far? That meant that this guy right here is pi. Well, if pi is all the way from here to here, then this is 2/3 of pi. 60 would be 1/3 of pi. 120 would be 2/3 of pi. And then 180 would be like 3/3 of pi. And all the way around the circle would actually be 2 of whatever pi is.
Why do you only compare it to 180 degrees, like to just pi, not 2 pi? Because 2 pi is the whole circle, so why aren't you comparing it to the whole circle?
Usually because the negative half is, in so many examples, irrelevant. Because you don't usually need to go into the negative quadrant. I guess for other reasons is it's probably easier to see that if this right here is whatever pi is defined as, then I can kind of see that like this is 1, this is 2, this is 3 in terms of like thirds, like it's been broken up into thirds. So therefore it's 2/3 of pi. I guess what I could do is I could keep going around the circle here and then say 4, 5, 6. I could break it up into sixths. But then really what I would have is like this would be 4/6 of 2 pi, which then would this would be 2. It would be 1, 2. It would be 2/6 of 2 pi, which then would be like 1/3 of 2 pi. But then if you were to like ignore the 2 here, then really it's like 2/3 of regular pi. I don't know if that makes sense. I think probably that's making it worse now.
Take another whole.
Yeah, okay.
I just don't get how you can go from, okay, 120 times 2 pi divided by 360 gets you 2/3 pi. That just doesn't stick in my head right now.
You be patient.
Yeah.
It's the hardest thing about this is now retraining your brain. Okay, let me try one more example, then we're going to take a break here. Okay, let's try this for 153 degrees. Before I do that though, first question for you. If you guys were to sketch 153 degrees, where would that approximately be? It's going to be most of the way over here. So let's say that this was the slice of pie that you were eating. This person is very greedy. They're almost eating half of the pie.
So it's smooth.
Okay. Okay, so this would be 153 degrees. In terms of not the whole pi, but actually pi the number, if this is 0, and this is a half of pi, and this is pi, how many radians is this going to be? Well, it's not going to be a full pi radian. That makes sense? It should be slightly less than that. How many radians itself, though? Well, you should probably be able to fit at least one, probably two. It's probably 2.5 of those 57 degree slices of pie. That makes sense? So now let's try the math on it. Take 153 degrees, and there are 2 pi radians in a full circle. What do you get?
17/20th pi.
Oh, sorry. Can you just give me the decimal number first, though?
0.85.
What was that?
0.85.
2.67.
That's what I was hoping for.
Oh, it's a pi.
Sorry, don't take pi out just yet. I'll do the taking the pi out thing in a second.
Why is the pi out?
Because 2.67 means that there's 1, 2, and probably 0.67 of this perfect slice of pie.
Okay.
But that being said, this number here is not that useful to us as a decimal number. So the more common way of writing it is what you guys already did,
Just divide it by pi.
which was to remove pi, or not times by pi in the first place. So if you were to then not put pi here and go 153 times 2 over 360,
Megan, of course, please come to the office. Maggie?
and then do fraction, what did you guys get then? 17 over 20, but then bring pi back in now.
Could you just get that 2.67 and divide it by pi?
Sure, but why times by pi in the first place then?
Good point.
You're right, though. You could. What this means then is that if this is 20 over 20 pi, this right here is 17/20ths of the way there. That's clicking. Amy.
Can we not go 153 because that's what we have
Yeah.
over the 57, which is 1 pi?
And just like times by that 57 degrees.
No, could we
Or,
not
yeah,
just
divide by it. That'll work. The only problem is that 57 degrees is like an approximation. It was a rounded value. So it's better to, rather than timesing by 57, do the whole 360 over 2 pi thing. Or the 2 pi over 360. Let's keep going here. I want to see if I can help this sink in. By the way, if this doesn't sink in by the end of the day, please don't freak out. It's like learning another language. It's like all of a sudden I'm teaching you in French. It's going to take a while to sink in, okay? Please don't freak out. Let's say I gave you radians, 5.27. What that means is you have 5.27 perfect slices of pie. If I were to draw that then, let me just draw a picture here. Get rid of all this stuff. So here's a pie. Here is like one slice of pie. Here's like your second slice of pie.
Could be like
Here's your third one. Here's your fourth one. Here's your fifth one. And then it was supposed to be like 5.27?
6.
No,
6.2.
What are you talking about? 5.27.
No. I was talking about this one right here. Sorry. 6.28 would be the whole thing though. Okay. So does that make sense that all the way, oh my goodness, all the way around here is 5.27?
so like 310.
It should be 300 something degrees. Here's how you prove it. Take 5.27, but now multiply by 360 degrees and divide by 2 pi, but put 2 pi in brackets. Otherwise your calculator will divide by 2 and then multiply by pi, but you want to divide by both of them.
To get like 2,000.
Yeah, and hopefully if you do this right, you get about 302 degrees.
Yeah. Do we have to put that fractions or anything?
No, because degrees is normal, but radians normally goes to fractions. Does that make sense though, that it's about 302 degrees all the way around there? I would say, yeah, that should be almost all of the circle. That work? Okay. To be honest though, rarely do we work with radians as a decimal number like this, because they usually have to get rounded. Normally I'm going to give you something like this, 5 pi over 6. So before I actually even draw this guy out here, 5 pi over 6, if I draw my circle again, here's 0, and this is pi. What we're really asking you for is 5/6 of pi. So like this could be 1/6, 2/6, 3/6, which by the way is half, 4/6, 5/6, and right here this would be 6/6. Does that make sense? So 5/6 of pi would be all the way up to here. Okay. Well, now let's try converting that using the formula I gave you. So go 5 pi, really it's 5/6 pi, multiply by 360, and divide by 2 pi. Just so you guys know, this pi right here can technically cancel with that pi right there. So what you really have to do is 5 times 360 divided by 6 and 2. Anybody get an answer for that? 150. Which hopefully makes sense. Shouldn't that be about where 150 goes? 5/6 of the way to 180 should be 150. Let me just do one more here. 3/8 of pi. So if I were to draw out a bit of a circle here, if this is 0, and that's half of pi, which would be 4/8, and this would be pi, which would be 8/8. 3/8 of pi should be somewhere in here. Does that make sense? So I know this should be less than 90, because 4/8 would be half, but this is only 3/8. So then 3 pi over 8 times by 360 over 2 pi. Pi should cancel, and I believe you get 67.5 degrees, which hopefully that makes sense, that's 67.5 degrees.
So for 17, would there be like 3 and that would be in like 2 pi over 8? Would that be like the whole thing?
We can have things that go like more than pi, and we can go down to this bottom quadrant. Like that's valid too. Should I do an example of that? Okay, let me do one more example then. Well, let me just extend the page, I guess. Okay. What if I were to say convert 11 pi over 6 into degrees?
Can the following students please come to the office? Kayla Davis, Caitlin Fournier, Micah Fox,
Almost.
Josh Marsh, Brett Neal,
Okay, well,
Seth Northhagen,
11 pi
and
over
Jacob
6
Williams.
times
Please come
by
to the office.
360 over 2 pi. What do you get? 330? Let's see if this makes sense. If this is 0, then this would be pi. Pi really would be 6/6 of pi. Then this would be 7/6, 8/6, 9/6, 10/6, 11/6, and all the way around the circle would be 12/6. But 12/6 is really 2 pi. Because really all of these are in terms of pi now. So does it make sense that 11/6 is 330 degrees? Hopefully it's kind of sinking in here. Okay. Let me give you guys some problems then. I'm going to skip ahead to this example here. This was an old diploma question. I'll give you a second just to read it first. So you've got this field,
Would it speak?
and this field right here is got 30 meters on this side here, 30 meters on this side here, and we're going to look for the distance around the back and add those 3 distances. So really our answer is going to be 30 plus 30 plus question mark, with question mark being the side right here.
Are we allowed to use?
It's not a perfect triangle though, it's an arc length. So unfortunately cosine law doesn't work for that. Cosine law would be if you went directly across.
No, it would be nice.
So,
Yep, we can do
after
that.
that now,
Wait, show.
Okay? Okay.
See, Chris.
There's-
Okay. You can find, what is that? Is that edge A?
This edge right here would be known as an
So you're
A.
gonna go your radiant times your angle.
Good. Now, can you tell me what you were looking at on your sheet there first, though? You have a formula I think you're looking at.
Yeah.
I see a lot of
It's
formulas.
theta equals A over R.
Yeah, there's a formula here. Theta equals A over R. Your radius, and Amy, you asked this earlier, the radius should be the same for both of them. Otherwise, something's wrong. This arc length is what we're looking for. So how do you find the arc length?
Multiply it by.
Multiply up the R by the theta.
So 97 times 30.
Well, here's the issue though. This theta right here
Oh.
has to be in
Radians.
radians. So first thing we should do is take 97, and my question for you is, how many perfect pieces of pi is 97? It should be more than one. So multiply by 2 pi, divide by 360. Now go ahead and use the decimal number, that's fine, just don't round it though. 1.6929. Okay, and then we have to make that your theta. So then times that by 30 to get your arc length. Okay, so 51 meters.
Oh,
But then you got to go 30 plus 30 plus 51. So 111?
What? Wait, so
Okay.
why did... Okay, so just...
So we times 97 by 2 pi over 360 to make radians.
yes.
And you got
I
1.69
get
radians.
that. I'm just wondering why the heck we just did all that stuff on the last page, taking out pi, we're not taking out pi right now.
Well, because in this example here, I could have then turned it into like a pi example, but I was going to take that number and times it by 30 anyways. So whether this answer right here didn't have pi in it or not didn't really make a difference. But if I hadn't have been timesing by the 30 later, often it's referred to as like how many portions of pi you have. Birdie.
Okay, so I understand how we got to 51. How did we get number 5?
Because you have to add this 30 and this 30 and this 51 to get the total length of sidewalk.
Oh, okay. Right. I just want to get the one side.
Okay.
Make math easy.
Okay, another example here. This is a little more physics-like for some of you in my physics class. Radius of the Earth.
Well, we know what that is.
Well, this isn't Earth, this is a small planet. So,
Is it just an earth?
this is an Earth. Okay, so what we've got here is 55 degrees, apparently is how far the plane has flown from here to here. And I told you, can you guys see that 55 in there, or did that not show up well?
It's there.
There's a 55 hidden in there.
Oh, yeah, I see it now.
The question here then is, what is the height of the satellite above the surface of the Earth? So basically what we're looking for is we're looking for from here to here, we're looking for that height.
What's the distance? Is that the little?
The distance is going to be your arc length.
So it'd be K wall solve.
Okay, so let me start with this formula here. Theta is equal to your arc length divided by your radius.
And then radius is arc length over theta.
So sure, radius is equal to arc length over theta. Well, our arc length is 8952, but I don't just divide it by 55 because 55 is in degrees. So don't do this. Take 55 degrees and times by 2 pi over 360. Now, if you want to write this in terms of pi, that's fine. But since it's a decimal number, we're going to end up dividing it anyway. So just find it as a decimal number. Kayla.
Will we always use 2 pi over 360?
Yes, that is the conversion ratio. So it should be just less than a radian, right? Like 0.8 or 0.9 maybe? So then take your 8952 and divide by 0.59.
Yeah, you did.
Because that would then get you your radius. Because it was,
Oh, that'll get you your whole rate.
Yeah.
Okay, what happens when you take 8952 and divide by that radians value? What'd you get?
9,325.66.
Okay,
Then would you just subtract?
because to get radius by its
Subtract the radius.
because from this formula here to get radius by itself, I brought radius up here and brought theta down to rearrange for arc. So then I took my arc length and divided by the radius the radians value, which was this one right here.
326.
So then we found the radius. Now how do we determine?
Okay, well the radius is this whole thing right here is 9325, but then the actual radius of the planet was 5,000. So to find the height, subtract 5,000.
How did you? Where did you?
See.
Oh.
Does that make sense? Because the radius right here said it was 5,000. So subtract this 5,000. And you said it was C?
4326.
Okay. So, are you okay with the 9325 number? Or that one doesn't make sense?
Like, I got 0.95, but I converted it to.
Okay. So then take your arc length. Like here, in this formula here, Amy, this value right here is 8952. This value here is 0.95, so. And our goal is to get radius by itself. So to get radius by itself, bring radius up here, bring theta back down, and divide the two numbers. And that'll give you R. Because we wanted to figure out the actual height of this from here to here. And then this part here was already 5,000. When you divided by 0.95, you should have divided by like 0.95, etc.
Oh, yeah.
How's it going? Give me a thumbs up, down, or somewhere in between. How comfortable are you with this so far? 45-degree angle, which is pi over 4, by the way.
So like pi over 8 be 22.5.
Yep. Okay. Okay, one last thing, then I'll be done for the day. The last term I need you guys to know is called a coterminal angle. Did I talk about this term last year with you guys? Okay, a coterminal angle really refers to an angle with different measures, but that have the same terminal arm. Let me give you an example here. From here to here, what was that? Okay, this right here should be pi over 2. I screwed up, this shouldn't be pi, this should be pi over 2. If I go positive around the circle pi over 2, it's the same thing as going backwards around the circle, negative 3 pi over 2. And that takes a little while to get your head wrapped around because half of pi and 1.5 pi add up to 2 pi, which is the full circle. Or another way of looking at it is this is 90 degrees, this is negative 270 degrees, and they add up to give 360. What was that? So this angle, I could call this angle 90 degrees. I could call this angle pi over 2. I could even call this angle negative 3 pi over 2. They all mean the same thing. So 90 degrees means pi over 2, also means negative 3 pi over 2. They all mean the same thing. That's called coterminal. So it's like the same angle written in different ways. Here's another way you can change coterminal angles. What if this was 130, and then I went around the circle an extra time, and I made it 490? Those would also consider to be the exact same thing, because the angle will still be in the same spot. Let me show you an example of a diploma question. So here's an old question from back in the day. All of the following are coterminal to 150 except for which one? Okay, so let me walk you through how you might solve this. Where would 150 be? around here. That's about 150. Okay, negative 930. Well, we could go backwards around the circle, I guess. So what if you were to, rather than go positive 150 this way, what if you would have gone the other way around? What would that be? It would be negative 210. But if you went around the circle another time and you like subtracted 360, then you'd get up to negative 520. And if you did another negative, no, 370, you did another 360, I believe it would get you to negative 930. So this one just means that it's the same angle, but going backwards and going around the circle a few times. So that one is coterminal.
Would you just be able to like add 360 and 930 to see if it would?
Sure, that's a good way of doing it. If you did negative 930 and you added 360 and you added 360 and you added 360, I think it should equal 150. Does that make sense? So one of the ways you could have a coterminal angle is by going backwards around the circle. It's the same angle, it's just you've gone around the circle a few times. This guy right here, I'm going to have to convert by using that rule I just showed you, which is 360 over 2 pi. So 17 pi over 6 times by 360 over 2 pi. Anyone get an answer for that?
150. No.
Divided by
It's 510 or something.
510.
Yeah. And then subtract 360.
Okay, well 510 just means you went around the circle a few too many times. So if you were to subtract 360, you get 150. So therefore, this one is also correct. I'm running out of room here.
That means that C this part.
Yeah, you're a little ahead of me, Nicole. 23 pi over 6, Nicole over here is a little ahead of me, I think. Then if I times this guy by 360 over 2 pi, what do you guys get for an angle if you do that? Anybody done that yet? So for the third one, take 23 pi over 6 and times by 3.
690.
Okay,
I think that's
so then 690 means you went around the circle a few too many times, so subtract 360.
330.
That would be 330. If you were to subtract 360 again,
Negative.
that would give you like negative 30 degrees. Neither of those are the same thing as 150, so that one didn't work. We should check the last one though, just to double check though.
But it's like really close. It's like
So negative 3.67 radians. If I were to times that by 360 and divide by 2 pi,
wait, what do you mean? What do you mean the other way? It's like negative 210.
so for this last one here, I'm going to take negative 3.67 radians times by 360 over 2 pi and get it into degrees. This time around, I have to keep pi as part of the equation though.
I got decimal.
You should get negative something though, right?
Why do we have to keep pi?
Because on like this one right here, when it was 23 pi over 6, pi could cancel. This one right here, we don't have pi as part of it. Did you guys get negative 210?
Yeah, and then add.
And then negative 210 really is the same thing if you add 360. It is 150. It's just gone backwards.
It's
Amy, the reason why we, like, on the previous examples here, see how there was like 17 pi over 6? And there was like a pi that could actually cancel here or cancel here. Well, this one here as a decimal number didn't have pi accounted for. So we can't cancel out pi because there isn't one to have it. So like this is the one where it's written as a decimal, whereas this one's written as a fraction.
So if it's written as a fraction, you radian, when you write it to degrees, you don't have to.
You can just get rid of pi. But if this one, yes. Okay, why don't I call it a day here? I think that's enough for right now. Here's what I need you guys to know. Okay. We worked really hard last year working with angles in standard position. But normally the angles were 0 degrees, 30 degrees, 50 degrees. Okay, guys, give me your attention. I'm almost done, okay? The new twists now are, one, you can go around the circle more than once. Just means that you get like 390 degrees. That's fine. You can even go backwards around the circle. Means you get a negative number. But probably the most tricky thing to work with is now how to convert to radians. because that's the expectation, unfortunately. I know it sucks, but that you're going to work with radians. Okay. You can write radians a couple of different ways. You could write radians as like 2 pi over 3 radians. 2 pi over 3 then means that if this is where pi shows up, 2/3 of pi would be right there. That's one way of writing it. I could also say that you have 1.523 radians, which just means that you'd have to figure out like if that is 1 perfect radian and that's like 2 perfect radians and it's sitting somewhere in between there. It's not hard to convert, but you just need to know the ratio. You either do 360 over 2 pi, or you do 2 pi over 360. Okay. You guys just need practice converting them. Okay. So I know there's not a lot of time left today, but if you get a chance, please try some of these questions on this page. Okay, I won't be giving you an assignment for a while, but over the next like couple of days here, and especially over like the long weekend, practice getting used to converting to radians. Okay.
Is there gonna be a whole lot of word problems?
No, not really.
Oh, good.
Not really. That's the hardest part is like converting your brain though to like